You let your breath slow as you picture a calm stretch of empty space, a place with no sound, no wind, and no matter to disturb its stillness. You imagine this space not as a backdrop but as something with structure, a quiet fabric that extends in every direction. You are sensing spacetime, the combined framework of space and time that forms the stage for every physical event. You notice how it holds its shape gently when nothing passes through it. You also notice that this framework is not fixed, because even emptiness has the ability to curve when mass or energy is present. You settle into the idea that gravity arises from this curvature rather than from any pulling force. You rest with the understanding that this idea forms the foundation of modern physics. You let it feel simple and steady, a slow beginning to a larger scientific journey. You allow a single object to appear in that emptiness, maybe a sphere with the mass of a star. You watch spacetime adjust around it, bending softly in response to its presence. You see that the object does not send out a force that tugs at anything else. Instead, the curvature itself guides how nearby objects move. You picture a smaller object placed near the larger one and observe it following the curved geometry without being pushed or pulled. You begin to feel how gravity works as a path that matter naturally follows. You recognize that this is the central idea of general relativity. You see how this view replaces the traditional notion of a force reaching across space. You rest in the clarity that curvature explains motion with calm simplicity. You let the picture grow more familiar as you breathe. You recall that Albert Einstein developed this description through equations that relate mass and energy to the curvature of spacetime. You imagine those equations shaping the geometry around every object in the universe. You understand that the mathematics predicts not only gentle curvatures but also extremely steep ones. You sense that when enough mass is packed into a small region, the curvature becomes so extreme that not even light can escape. You realize that this is how a black hole forms in the language of general relativity. You observe how nothing about it requires speculation or exaggeration. You appreciate that a black hole is simply the natural outcome of matter collapsing under its own gravity. You let the idea settle quietly, without fear or drama. You sense how straightforward the prediction becomes once curvature is understood. You picture spacetime near a black hole growing steeper as you move inward. You see that the slope is not physical in the usual sense but a way of visualizing how motion is guided. You notice how time behaves differently in regions of strong curvature. You remember that time passes more slowly near massive objects, an effect confirmed through experiments and observations. You feel the quiet precision of these ideas, supported by measurements of clocks on satellites and by the behavior of light signals near large bodies. You begin to understand why the environment near a black hole is dominated by these changes. You see how the geometry determines every possible path. You rest with the awareness that curvature shapes not only motion but also the flow of time itself. You allow this to deepen your sense of gravity as a geometric phenomenon. You now take a step back in your imagination and consider the universe on a larger scale. You see stars, planets, gas clouds, and galaxies all bending spacetime according to their mass and energy. You notice how gravitational lensing reveals this curvature by bending the path of distant light. You remember that telescopes have captured images of light distorted around massive clusters. You recognize these arcs and stretches as direct evidence of spacetime curvature. You appreciate how the universe provides observation after observation that matches Einstein's predictions. You feel a calm confidence in the reliability of these measurements. You understand that gravity, though gentle in many situations, shapes the structure and behavior of everything you see in the night sky. You let this understanding feel steady and grounding. You shift your attention toward extremely dense objects, such as neutron stars and black holes, where curvature becomes far stronger. You observe how their density, rather than just their mass, intensifies spacetime distortion. You note that a relatively small object can create extreme curvature if its mass is compressed tightly enough. You see why a collapsing star can reach the point where an event horizon forms. You learn that this boundary marks the region where paths through spacetime all move inward. You understand that nothing inside the horizon can follow a path leading outward. You realize that this is not because the black hole pulls things back, but because the geometry allows no other direction. You let the simplicity of this explanation replace any earlier images of suction or force. You recognize it as a clean and quiet description rooted in general relativity. You imagine adding a second black hole nearby. You observe how the two curvatures interact, creating a shared geometry between them. You see each object following the shape created by both masses. You feel how this motion requires no pushing or pulling. You notice how their orbit emerges naturally from the geometry. You see that if they lose energy through gravitational waves, their paths slowly draw closer. You sense that this entire process is guided by the curvature rather than by any external influence. You appreciate that binary black holes arise in the universe through this simple set of rules. You let the idea remain gentle and factual, held together by the quiet logic of spacetime. You return to the broader idea of gravity as a natural, continuous feature of the universe. You feel how the curvature of spacetime shapes every orbit, every fall, and every rotation. You reflect on how objects move not because they are pulled but because they follow the geometry laid out for them. You sense the elegance of this idea, confirmed through decades of experiments, observations, and precise measurements. You recognize how it unites the behavior of planets with the behavior of light and time. You let this unity bring a feeling of calm coherence to your understanding. You rest in the knowledge that general relativity has become one of the most tested theories in physics. You take a slow breath and imagine once more the quiet fabric of spacetime extending around you. You let the image grow smooth and ordered, shaped softly by the matter within it. You realize that even the most extreme events in the universe, including the merging of black holes, are built on this gentle foundation. You see that the curvature of spacetime provides the language needed to understand those events without exaggeration. You allow this awareness to settle into a steady rhythm. You let the universe feel calm, even in its most powerful moments. And in this calm, you begin to notice how two massive objects can shape the geometry together, gradually drawing closer as the fabric around them responds. You begin by imagining a massive star, hundreds of times larger than the sun, burning steadily in the quiet of space. You feel the long balance between gravity pulling inward and pressure from nuclear fusion pushing outward. You sense the gentle, persistent energy released as hydrogen fuses into helium, then heavier elements, layer by layer. You notice how each stage of fusion creates a slightly denser core, slowly changing the distribution of mass within the star. You feel the patience of this process, taking millions of years, while energy radiates outward as light and heat. You recognize that the star's life is governed by well-understood physical principles: thermonuclear reactions, radiation pressure, and gravitational equilibrium. You rest with the knowledge that every massive star follows these rules, shaping its environment even before any collapse occurs. As the star exhausts its nuclear fuel, you see its core no longer able to resist the pull of gravity. The outer layers begin to fall inward while the core contracts rapidly. You watch the collapse accelerate, increasing the density of the central region to extraordinary levels. You note that for stars above a certain mass, nothing can halt this contraction, and a singularity forms at the center. You understand that a black hole appears naturally from this process, defined by an event horizon, the boundary beyond which no information escapes. You feel the precision of these ideas, confirmed by decades of astrophysical theory and observation. You sense the continuity of the process. Massive stars give rise to stellar mass black holes, entirely explained by gravity and nuclear physics. You notice that not all black holes start at the same size. You learn that stellar mass black holes typically range from a few to tens of solar masses, formed directly from collapsing stars. You then let your mind expand to intermediate mass black holes, which range from hundreds to thousands of solar masses. You understand that these objects may form through mergers of smaller black holes or through direct collapse of massive gas clouds. You also consider supermassive black holes, millions to billions of times the sun's mass, residing at the centers of galaxies. You recognize that their origins are still under investigation but involve slow accumulation of matter, repeated mergers, and long periods of accretion. You feel the continuity in how all these objects grow from mass and energy, obeying the same gravitational principles at different scales. You watch as matter begins to gather around a newly formed black hole. You see gas and dust spiraling into an accretion disk, orbiting rapidly due to conservation of angular momentum. You observe friction and turbulence heating the disk, emitting X-rays that can be detected by space-based telescopes. You notice how astronomers use these X-rays to confirm the presence of black holes in binary systems and galactic centers. You understand that accretion is an efficient way for black holes to grow, slowly increasing their mass over millions of years. You sense the rhythm of this process, steady and predictable, with energy released into the surrounding environment. You appreciate that these observations provide strong evidence for black hole formation and growth, linking theory and experiment seamlessly. You follow a black hole in a binary system, paired with a massive companion star. You watch material flow from the star toward the black hole, forming an accretion stream. You see the X-ray emissions vary as the flow changes, allowing astronomers to measure mass and spin indirectly. You notice how gravitational interactions between the two bodies affect their orbits, creating subtle shifts that can be detected with precision. You understand that these dynamics are not chaotic but governed by the same geometric principles of spacetime you observed earlier. You rest in the knowledge that even complex systems, like binaries with mass transfer, can be explained through careful measurement and theory. You imagine multiple black holes existing within dense stellar clusters or galactic cores. You see how gravitational interactions gradually lead some of them to pair up, forming binaries. You notice that these binaries can merge over time, producing more massive black holes. You recognize that this hierarchical growth is responsible for some intermediate mass black holes and contributes to the population of supermassive black holes in the centers of galaxies. You sense the slow, patient nature of these processes, unfolding over millions or billions of years. You appreciate that the universe allows such growth to occur in a predictable way, following gravitational laws precisely. You feel calm in the understanding that even dramatic mergers are entirely natural. You shift your attention to observational techniques. You notice that astronomers use both electromagnetic and gravitational signals to detect black holes. You watch as LIGO and Virgo record minute distortions in spacetime caused by black hole mergers. You see how X-ray observatories, such as Chandra, measure high-energy emissions from accretion disks. You understand that each method provides complementary information, confirming mass, spin, and distance. You recognize that these measurements are not speculative. They rely on extremely precise instruments and well-tested models. You let yourself absorb the sense of meticulous, careful science guiding every discovery. You consider how the environment around a black hole evolves. You notice that accretion disks can feed relativistic jets, collimated streams of particles moving near the speed of light. You see that these jets can extend for thousands of light years, interacting with surrounding gas. You understand that jets are not mysterious but arise from the interaction of magnetic fields and rotating matter near the event horizon. You appreciate that these phenomena, while energetic, are consistent with known physics. You feel the gentle consistency of these processes, where extreme events still follow comprehensible rules. You follow a black hole over cosmic time, observing how it slowly gains mass through mergers and accretion. You notice that supermassive black holes, millions of times more massive than the Sun, anchor galaxies and influence their evolution. You understand that their gravity affects star formation, gas motion, and galactic dynamics. You recognize that even on these scales, the underlying laws remain the same. Spacetime curvature, energy conservation, and general relativity govern motion and growth. You feel the continuity of physical law across vast distances in time. You sense the calm inevitability of these processes, unfolding quietly throughout the universe. You now reflect on the diversity of black holes you have seen. You sense the elegance of a universe where objects grow in size and mass through accretion, collapse, and merging, all described by consistent, observable rules. You recognize that every massive black hole began as a star, followed by predictable evolution and interaction. You feel the precision and reliability of the science, grounded in observation and calculation. You rest with the awareness that these objects, which seem distant and extreme, obey the same natural laws that guide motion and time elsewhere. You sense the steady, patient accumulation of mass shaping the universe at every scale. And as you breathe slowly, you notice how these growing black holes, guided by gravity and curvature, can eventually influence one another's paths, beginning the subtle dance that may lead them into a shared orbit and the slow, measured approach of a cosmic encounter. You allow your mind to drift toward regions where stars are densely packed, such as globular clusters or the centers of galaxies. You sense how gravity governs every motion, pulling objects subtly toward each other. You notice that in these crowded environments, interactions between stars and compact remnants occur more frequently than in isolated space. You see that black holes, remnants of massive stars, can slowly encounter each other as their paths cross. You recognize that chance and motion, guided by gravitational laws, make the formation of binary black holes more probable in these dense regions. You rest with the understanding that the universe favors these pairings where conditions allow repeated encounters over long periods. You observe the first stage of pairing. Two black holes may pass near each other, exchanging energy with surrounding stars. You notice how gravitational interactions slightly adjust their velocities and orbits. Over time, repeated encounters remove kinetic energy from the pair, allowing them to settle into a bound orbit. You understand that this process is entirely natural, relying on fundamental conservation laws of momentum and energy. You see that the pairing is gradual, almost imperceptible in human terms, but significant across millions of years. You feel the quiet patience of gravity, sculpting the paths of these dense objects with precision. You let your attention focus on galactic centers, where supermassive black holes and dense star populations coexist. You notice that stellar mass black holes here have higher chances of interacting due to proximity and the influence of surrounding mass. You understand that dynamical friction, the process by which moving objects lose energy through gravitational interactions with nearby matter, facilitates the approach of black holes toward one another. You sense the long-term stability of these interactions, allowing two black holes to form a binary without sudden disruption. You recognize that this environment, although extreme, still obeys the same geometric rules of spacetime and energy conservation you have already explored. You now picture the orbit of a newly formed binary. The black holes circle each other, their paths determined by the curvature of spacetime they create together. You notice that orbital energy gradually radiates away in the form of gravitational waves, ripples traveling through spacetime. You understand that this emission is subtle at first, almost imperceptible, but persistent over millions or billions of years. You observe how the separation between the black holes slowly decreases, drawing them closer together. You feel the steady rhythm of their motion, guided entirely by the geometry of spacetime and the laws of physics. You imagine the influence of additional objects nearby. Other stars, black holes, or gas clouds can perturb the binary's orbit, changing eccentricity or inclination slightly. You notice that these interactions, though small, affect the long-term evolution of the system. You understand that over time, gravitational interactions tend to stabilize the binary, funneling energy outward and tightening the orbit. You sense the universality of these processes. Even in seemingly chaotic environments, predictable physical laws govern the approach of black holes. You rest with the awareness that the universe carefully balances energy and motion in a quiet, precise manner. You let yourself consider the timescales involved. You realize that the formation and tightening of a binary can take millions or even billions of years. You notice that these durations are natural when compared to the speed of light and the distances between objects. You understand that the universe operates on scales much larger than human experience, and that patience is a feature of cosmic processes. You feel the calm reassurance that every change in the orbit follows known laws, measurable and consistent. You observe how slow accumulation of small effects leads to the eventual inevitable closeness of the pair. You now focus on the orbital dynamics themselves. You notice that the black holes follow elliptical paths initially, gradually circularizing as energy is lost through gravitational waves. You understand that this is a consequence of general relativity and the emission of energy according to the quadrupole formula. You see that the orbital period shortens as the separation decreases, increasing the frequency of their motion. You appreciate that each revolution is predictable and measurable in theory, and that precise simulations can track these orbits accurately. You feel the gentle certainty in these calculations, supported by observational evidence of distant black hole binaries. You watch the subtle signals emitted by the pair. Though electromagnetic radiation is usually absent in vacuum, gravitational waves carry energy outward. You notice that as the orbit tightens, the waves become stronger and more detectable. You understand that the earliest emissions are weak and long-period, almost imperceptible even to sensitive detectors. You sense the quiet accumulation of these waves across time, gradually removing orbital energy and allowing the black holes to approach closer. You rest in the continuity of the process, knowing that nature operates consistently and without sudden surprises. You let your mind observe how conservation laws shape the system. Angular momentum and energy remain constant overall, even as gravitational waves carry energy away from the orbit. You notice how the binary maintains equilibrium while gradually adjusting to the loss of energy. You understand that these fundamental principles govern every interaction, ensuring predictability and stability. You feel the steady hand of physical law guiding the motion, creating an ordered path in what might seem like a complex environment. You sense the universe's quiet commitment to consistency, where even extreme objects obey clear rules. You now take a broader perspective, seeing multiple binary black holes forming across the cosmos. You notice that some will merge quickly, while others will remain separated for eons. You understand that the conditions for pairing, density, mass, and proximity determine the likelihood and timing of eventual merger. You feel the vast scale of time and distance, and the slow, careful shaping of binary systems by gravity. You appreciate that each pair is a natural product of stellar evolution, environmental factors, and the fundamental geometry of spacetime. You rest in the calm orderliness of these processes. You consider how scientists identify these systems. You see that indirect evidence, such as X-ray emissions from nearby accreting material, can suggest the presence of one black hole. You understand that statistical models and simulations predict the number of binaries in various environments. You feel the quiet certainty that these predictions match observations from telescopes and gravitational wave detectors. You sense the gentle satisfaction of knowing that theory and observation align, describing the gradual pairing of black holes accurately. You rest with the knowledge that this pairing is a predictable step in the life cycle of massive objects. You now notice the binary system as it stabilizes into a long-term orbit. You feel the rhythm of their motion, slow and precise, entirely dictated by the curvature of spacetime they create together. You sense that, although distant and unseen, the pair is quietly preparing for eventual inspiral. You understand that this process is continuous and deterministic, governed by general relativity and the emission of gravitational waves. You allow yourself to rest in the calm logic of their approach, knowing that these interactions, while subtle, shape some of the most extreme events in the universe. And in this steady, measured motion, you begin to feel the gradual tightening of their orbit, the persistent whisper of gravitational waves hinting at the profound energy that will carry them toward an inevitable, transformative union. You begin by focusing on the binary black holes circling each other in their shared orbit. You notice that the motion is smooth, governed entirely by the curvature of spacetime, yet subtle changes are constantly occurring. You become aware that these objects are not isolated in a perfect vacuum. Even in empty space, the geometry itself can carry energy away in the form of gravitational waves. You sense that this is a gentle, continuous process, imperceptible without extremely sensitive instruments, but inexorable in its effect. You understand that as energy radiates outward, the orbit gradually shrinks, and the black holes move ever closer together. You watch how the waves propagate through the surrounding spacetime. You see them as ripples expanding outward from the orbit, carrying information about the masses, spins, and motions of the black holes. You note that these waves travel at the speed of light, stretching and compressing distances very slightly as they pass. You understand that although the distortions are tiny, they are measurable with modern detectors on Earth. You appreciate the precision and sensitivity required to detect these ripples, and you rest in the confidence that this phenomenon is predicted exactly by general relativity. You imagine the orbital decay over millions of years. The black holes circle each other thousands of times, losing just a fraction of their orbital energy with each revolution. You notice how the frequency of their motion gradually increases as the separation decreases. You understand that the process is slow because the energy loss at these separations is small relative to the total orbital energy. You sense the stability of the inspiral, each orbit predictable and steady, creating a calm rhythm in spacetime. You let yourself feel the patience of cosmic time, where immense energies operate at a pace almost imperceptible on human scales. You consider the equations that govern the inspiral. You see that the energy carried away is proportional to the masses of the black holes and inversely proportional to the separation to the fifth power, a relationship derived from general relativity. You notice how this explains why more massive binaries emit stronger waves and merge more quickly. You understand that the mathematics describes reality with precise accuracy, confirmed through observations of distant mergers. You feel the quiet power of these equations, which allow scientists to predict the behavior of black holes millions of light-years away with confidence. You now watch the orbital paths gradually tighten. The ellipses become smaller and closer to circular, while the speed of the black holes increases. You notice that even these subtle changes are accompanied by a slight increase in gravitational wave amplitude and frequency. You understand that this inspiral stage is detectable from Earth for the most massive or closest systems, once instrumentation is sensitive enough. You rest with the understanding that the universe allows these tiny, predictable changes to accumulate over vast stretches of time, eventually bringing the black holes to a stage where their motion is far more rapid and energetic. You take a moment to focus on the role of energy conservation. You notice that as orbital energy decreases, the total energy of the system is redistributed into gravitational radiation. You understand that nothing is lost. It is transferred outward through spacetime itself. You see that this radiation is remarkably efficient over time, slowly transforming a wide, stable orbit into a closer, faster one. You sense the inevitability of this process, guided entirely by physical law. You rest in the knowledge that every orbit, every passing second, contributes to the gradual spiral inward, measured and consistent. You imagine how different factors influence the inspiral. If the black holes are spinning, you see that spin-orbit coupling slightly modifies the paths, adding complexity to the emitted waves. You notice that any small eccentricity in the orbit gradually diminishes as energy is radiated. You understand that these details are captured in precise numerical simulations, which predict waveforms that match observations from detectors. You feel the quiet satisfaction of knowing that these simulations are grounded in real physics and confirmed repeatedly. You rest with the awareness that every small effect has been carefully accounted for in understanding this long journey. You focus on the observational evidence. You think about the detections made by LIGO and Virgo. You see how scientists compare observed waveforms with theoretical templates to confirm the presence and properties of distant binary black holes. You notice how the slow inspiral stage, while mostly undetectable initially, produces signals that can accumulate over days or weeks for the most sensitive systems. You understand that each detection allows scientists to verify the predicted physics of orbital decay. You sense the reassurance of this agreement between theory and measurement, and the certainty it provides about the nature of gravitational waves. You now consider the timescales once again. You realize that for widely separated binaries, the inspiral can last billions of years, while more compact binaries evolve more quickly. You sense the vast patience of cosmic time, where even the most powerful objects follow predictable rules over epochs far longer than a human lifetime. You notice that these slow changes are necessary for the eventual merger, laying the groundwork for the final, rapid phase of motion. You rest in the calm knowledge that these processes are orderly, measurable, and entirely consistent with the known laws of physics. You visualize the increasing frequency and amplitude as the black holes draw nearer. You understand that while the early inspiral is slow and subtle, the final thousands of orbits will become progressively faster, compressing time and space in their motion. You notice how gravitational wave signals rise in frequency and intensity, creating a crescendo detectable by sensitive instruments. You sense that these final moments, although still governed by the same principles, mark a transition from gradual stability to a more energetic and rapid evolution. You rest with the anticipation of the remarkable forces and motions that will soon dominate the system. You now reflect on the continuity of spacetime and energy throughout the inspiral. Each orbit, each ripple, is a testament to the predictable behavior of mass and geometry. You feel the elegance of a universe where even the most extreme objects operate within a framework that is measurable and exact. You sense how the slow spiral inward represents both the persistence of fundamental laws and the gentle accumulation of effects over time. You rest with the awareness that this steady approach will eventually lead to the intense, energetic stage where the black holes converge and the most powerful gravitational waves are produced. And as you observe the orbit tightening ever so gradually, you begin to sense the subtle crescendo in gravitational waves, a quiet but unstoppable reminder that these massive objects are approaching a profound and transformative encounter. You begin by imagining the spacetime around two orbiting black holes. You notice that as these dense objects circle each other, the geometry of spacetime itself subtly shifts and stretches. You understand that these distortions travel outward at the speed of light, carrying energy away from the system. You feel the calm regularity of this process, a continuous transformation of spacetime that does not require force or friction. You recognize that these ripples, called gravitational waves, were predicted by Einstein in 1916 as a natural consequence of general relativity. You rest with the certainty that this is a precise, mathematically grounded phenomenon, not a metaphor or poetic image. You allow your awareness to focus on the creation of gravitational waves by accelerating masses. You notice that the strength of these waves depends on the mass of the objects and the speed at which they orbit. You see that binary black holes, due to their immense mass and rapid motion, generate some of the strongest waves possible in the universe. You understand that any object in orbit produces gravitational waves, but most are far too weak to detect. You sense the gradual accumulation of energy carried away, and the resulting slow spiral of the black holes toward each other. You feel the predictable, calm nature of this energy transfer, entirely consistent with physical laws. You consider the shape and propagation of gravitational waves. You notice that they are transverse, stretching and compressing space perpendicular to the direction of travel. You see them as two polarizations called plus and cross, which interact with spacetime in subtly different ways. You understand that as the waves pass through any region, distances between points are altered by an extremely small amount, on the order of 1 part in 10 to the power of 21. You sense how extraordinarily precise detection must be, and how remarkable it is that modern instruments can measure these tiny effects. You rest with the knowledge that science can perceive even the slightest curvature shifts caused by distant black holes. You now imagine a gravitational wave detector such as LIGO. You see its long perpendicular arms, with lasers bouncing between mirrors at each end. You notice how a passing gravitational wave stretches one arm while compressing the other, producing a measurable interference pattern in the laser beams. You understand that these instruments are sensitive enough to detect changes smaller than the diameter of a proton. You feel the calm precision of this technology, which translates the minuscule ripples in spacetime into a measurable signal. You appreciate that these measurements provide direct evidence of waves generated by cosmic events millions of light-years away. You follow how the waves encode information about the sources. You notice that the amplitude of the waves reflects the total mass and distance of the binary, while the frequency reveals the speed of their orbital motion. You see that as the black holes spiral inward, the frequency increases, creating a chirp signal that is characteristic of merger events. You understand that these signals allow scientists to reconstruct properties of the black holes, including mass, spin, and orbital parameters. You feel the elegance of this process, where physical principles, observation, and careful measurement combine seamlessly to reveal distant phenomena. You now consider how gravitational waves travel through the universe. You notice that they move unimpeded by matter, passing through stars, gas, and galaxies without scattering. You understand that this property makes gravitational waves excellent messengers, carrying information about events that might be invisible in electromagnetic light. You see that black hole mergers, which emit little or no light, are nonetheless loud in gravitational waves. You feel the significance of this ability, opening a new window into the cosmos, and you rest in the calm reliability of the physical laws that govern their propagation. You turn your attention to the effect of wave amplitude and frequency on detection. You notice that stronger signals come from more massive or closer binaries, while lower mass systems produce weaker waves. You understand that as the black holes approach each other, the waves increase in both frequency and strength, eventually becoming detectable across vast distances. You feel the rhythm of this process, a gentle crescendo over millions or billions of years, culminating in a signal measurable on Earth. You rest in the awareness of the scale and subtlety of this natural process. You now imagine multiple black hole binaries across the universe, each sending gravitational waves outward. You notice that space is filled with a background of these ripples, though most are too weak to detect individually. You understand that merging black holes stand out because of their strong, coherent signals. You sense the precision of this natural ordering. Only the most energetic interactions produce detectable effects, yet every orbit contributes to the gradual shaping of spacetime. You rest with the understanding that even tiny contributions accumulate over cosmic time, reinforcing the predictable nature of gravitational wave emission. You focus on how simulations reproduce these signals. You see that numerical relativity allows scientists to model the full dynamics of orbiting black holes, including strong field effects near the event horizon. You notice that predicted waveforms match closely with observed data, confirming Einstein's equations under extreme conditions. You understand that these simulations are crucial for interpreting real detections, providing templates that allow instruments to extract faint signals from noise. You feel the calm reassurance of this agreement between theory and observation, the quiet elegance of accurate physical predictions verified by careful measurement. You now think about the gradual inspiral and the resulting energy loss. You notice that the binary loses a small fraction of its total energy with each orbit, steadily reducing separation and increasing orbital speed. You understand that gravitational waves carry this energy away, allowing the system to evolve naturally toward the moment of merger. You sense the universality of this process. The same principle governs all binaries, from stellar mass pairs to supermassive black hole systems. You rest with the quiet precision of this cosmic mechanism, knowing that it operates consistently and predictably across the universe. You reflect on the interplay between mass, motion, and spacetime curvature. You feel the balance maintained by general relativity, where accelerated masses shape the fabric of space and time while emitting energy outward. You notice how the binaries orbit, the emitted waves, and the gradual spiral inward are all interconnected through the same fundamental laws. You understand that these processes are not chaotic, but highly structured, governed by measurable, observable principles. You rest with the awareness of the calm, ordered behavior of black holes as they approach the final, energetic stages of their motion. And as you perceive the gentle but persistent ripples moving through spacetime, you sense the slow crescendo building, a silent but inevitable herald of the intense convergence and merger that will soon release the most powerful gravitational waves ever produced in the universe. You let your attention drift toward the black holes as they draw ever closer, feeling the subtle yet profound changes in the surrounding spacetime. You observe that each black hole is defined by a boundary called the event horizon, the surface beyond which nothing can escape, not even light. You notice that spacetime curves steeply near this boundary, guiding the motion of matter and light with precise mathematical predictability. You understand that the singularity at the center represents a point of extreme density where classical physics breaks down, but general relativity still predicts the surrounding geometry with confidence. You rest in the awareness that these features are not imaginary. They are fully consistent with decades of observation and calculation. You focus on the final orbits before the black holes touch. You feel how time itself behaves differently near the event horizon. You notice gravitational time dilation, where a clock near the horizon ticks more slowly relative to a distant observer. You understand that if you could observe a particle orbiting very close to the horizon, its motion would appear to slow dramatically from afar, while locally it would move normally. You sense the elegance of this prediction. It is a direct consequence of spacetime curvature, not an arbitrary effect. You appreciate how light escaping from these regions becomes increasingly redshifted, stretching to longer wavelengths as it climbs out of the deep gravitational well. You observe the behavior of matter and radiation near the horizon. Gas caught in the outer reaches of the accretion disk continues orbiting, producing high-energy X-rays visible to distant telescopes. You notice that as these particles approach the inner edge of the disk, their trajectories are warped, tracing paths defined entirely by the black hole's gravitational field. You understand that no information about objects crossing the horizon ever reaches the outside world, creating the apparent invisibility of the black hole. You feel a calm certainty in the consistency of this rule. The event horizon is absolute in its definition, and nothing escapes its grasp once crossed. You consider the curvature of spacetime more closely. You notice that the metric describing this curvature grows increasingly steep as the black holes approach each other. You see that tidal forces stretch and compress objects differently depending on proximity and orientation relative to the singularity. You understand that these effects are extreme but predictable, calculated precisely by Einstein's field equations. You sense that even in these violent regions, physics remains reliable. The rules governing motion, energy, and light remain consistent, just operating in more intense regimes. You follow a test particle falling toward the horizon. From a distant perspective, its approach seems to slow, almost freezing in time as it nears the edge. Locally, however, it falls with normal acceleration, obeying the same laws as elsewhere in spacetime. You recognize that this dual perspective, local versus distant, is a key feature of relativistic physics. You feel a deep reassurance in the clarity of these concepts, knowing that scientists can reconcile these differing viewpoints mathematically and predictably. You rest in the understanding that these effects, though extreme, are part of the continuum of gravitational phenomena. You turn your attention to light itself. You notice photons emitted near the horizon must climb out of a steep gravitational well, losing energy in the process. You understand this as gravitational redshift. The closer the emission point to the horizon, the longer the wavelength becomes by the time it reaches a distant observer. You sense the precision of this prediction, which has been confirmed through observations of stars orbiting the supermassive black hole at the center of the Milky Way. You appreciate that even as light bends and stretches near the horizon, the behavior follows exact rules derived from relativity. You now examine the final in-spiral motions. You see that as the black holes orbit each other in these tight trajectories, their speeds approach significant fractions of the speed of light. You understand that the combination of high velocity and intense gravitational fields produces the strongest gravitational waves yet emitted. You notice that the orbital period shortens dramatically, and each revolution releases increasingly powerful ripples in spacetime. You feel the rhythm of this motion, a steady increase in intensity governed entirely by the geometry of spacetime and the laws of motion, without randomness or chaos. You observe the interaction between the two event horizons. You notice how the spacetime around each black hole begins to distort the other's gravitational field. You understand that these distortions influence the shape and frequency of the emitted gravitational waves. You sense that the approach toward coalescence is not instantaneous but occurs in a predictable, gradual tightening of their mutual orbit. You rest in the assurance that every aspect of this motion, from orbital decay to wave emission, follows equations tested by numerical relativity and confirmed by observational data. You focus again on the singularity and horizon distinction. You notice that while the singularity remains hidden, the event horizon defines the observable boundary of the black hole. You understand that the physics outside the horizon is fully describable, while inside, classical equations break down. You feel the precision of this partition. The universe provides a region of calculable predictability right up to an absolute boundary. You rest with the confidence that this structure, though extreme, is a firm and well-tested aspect of relativistic astrophysics. You now reflect on time dilation, light bending, and space-time curvature together. You notice how these phenomena converge in the final orbits, producing both extreme gravitational wave emission and dramatic relativistic effects for any nearby matter. You understand that the interplay of these factors sets the stage for the rapid in-spiral and eventual merger. You feel the quiet inevitability of these processes, unfolding without exception according to known physical laws. You rest with the awareness that the universe operates with remarkable precision, even in its most energetic and extreme events. And as the black holes complete their final tight orbits near their event horizons, you sense the acceleration of spacetime ripples and the crescendo of gravitational waves, preparing the system for the sudden, intense phase of coalescence that will release extraordinary energy across the cosmos. You focus on the binary black holes as they enter their final seconds before merging. You notice the sudden increase in orbital speed as the separation between them diminishes dramatically. Each black hole moves at a significant fraction of the speed of light, completing multiple revolutions in a single second. You feel the intense, precise regularity of these orbits, guided entirely by the curvature of spacetime. You understand that this rapid motion generates gravitational waves of increasing frequency and amplitude, a crescendo of spacetime ripples that propagates outward. You sense the extraordinary energy involved, and yet it follows the exact predictions of general relativity. You observe the gravitational waves themselves. You notice the frequency rising steadily, from tens to hundreds of cycles per second, and the amplitude increasing correspondingly. You understand that this chirp signal is characteristic of the final inspiral phase. You see how each revolution contributes additional energy to the waves, causing a measurable distortion of spacetime that can reach detectors across billions of light-years. You appreciate the precision of this phenomenon. The waveform's shape, frequency, and growth are all predictable from the masses and spins of the black holes. You rest in the knowledge that the universe operates consistently even under these extreme conditions. You allow yourself to consider the physical forces involved. You notice that tidal interactions between the black holes become significant, producing additional distortion in their orbital paths. You understand that these forces, while extreme, are completely describable through Einstein's equations. You see that the interaction affects not only the emitted gravitational waves but also the angular momentum and spin alignment of the merging pair. You feel the calm order underlying these seemingly violent dynamics, as every motion and energy transfer adheres strictly to the laws of physics. You now examine how simulations track these final seconds. You notice that numerical relativity models account for the strong field regime near the event horizons, where nonlinear effects dominate. You understand that computers solve Einstein's field equations step by step, calculating the gravitational field at each point in spacetime. You see that these simulations can reproduce the waveform of the final inspiral with remarkable accuracy, matching the signals detected by LIGO and Virgo. You feel the reassurance of this agreement between theory and observation, confirming that the extreme physics of black hole mergers is predictable and measurable. You observe how the orbital period shrinks further. The black holes complete dozens of orbits in a single second, with orbital velocities approaching the speed of light. You notice that this motion produces the most intense gravitational waves yet emitted in the inspiral stage. You understand that the energy carried away by these waves continues to reduce orbital separation, accelerating the approach toward merger. You sense the rhythm of this rapid motion, a precise, steady acceleration, entirely determined by mass, spin, and spacetime curvature. You consider the effect on time near the black holes. You notice that time dilation reaches extreme levels. From a distant perspective, the motion seems almost frozen at the horizon, yet locally each black hole orbits normally. You understand that this is a consistent consequence of general relativity. Clocks in stronger gravitational fields tick more slowly relative to distant observers. You rest in the clarity of this effect, recognizing that the combination of high speed and strong gravity produces measurable, predictable changes in the passage of time. You now focus on the amplitude of gravitational waves. You notice how the signal strength grows as the black holes approach each other. You understand that the energy flux is proportional to the reduced separation and mass of the system, producing a steep rise in wave amplitude during these final seconds. You see that detectors on Earth can resolve these changes in real time, capturing the waveform of the inspiral with remarkable fidelity. You appreciate the quiet certainty of this measurement, which confirms both the existence of gravitational waves and the detailed predictions of numerical relativity. You observe the subtle influence of spin on the final orbits. If the black holes rotate, their spins interact with the orbital motion, slightly modifying the waveform. You notice how aligned spins increase orbital stability while misaligned spins can introduce precession. You understand that these effects, while small, are predictable and included in simulations. You rest in the knowledge that every variable, mass, spin, orbital orientation, is accounted for, producing waveforms that match observations with high accuracy. You consider the role of gravitational wave detectors in this phase. You notice that the high-frequency, high-amplitude signals from the final seconds of Inspiral are precisely what instruments like LIGO, Virgo, and CAGRA are optimized to capture. You understand that the signal-to-noise ratio increases rapidly during these moments, allowing confident identification of the event. You feel the meticulous care involved in separating true signals from instrumental noise, using matched filtering techniques and global network correlation. You rest in the calm precision of modern experimental astrophysics. You now imagine the cumulative effect of these waves traveling across space. Each oscillation carries information about the masses, spins, and orbital parameters of the black holes. You notice that, though the waves stretch across billions of light-years, they remain coherent, enabling reconstruction of the source. You understand that the final seconds before collision encode the most critical information, providing a clear fingerprint of the merging system. You sense the quiet elegance of this cosmic communication, entirely governed by the laws of physics, traveling unimpeded across the universe. You follow the approach of the event horizons. You notice how the distance between them decreases with every passing fraction of a second. You understand that each orbit in these final moments is faster and closer than the last, producing a nearly exponential increase in gravitational wave frequency. You see that this motion is precisely what simulations predict, with no deviation from expected physical laws. You rest in the knowledge that the rapid Inspiral, though extreme in scale and intensity, remains a calm, predictable process when described through relativity. You reflect on the entire final seconds of the Inspiral. You sense the convergence of velocity, orbital decay, gravitational wave emission, time dilation, and spacetime curvature. You understand that these combined effects create the conditions for the imminent merger, a brief but immensely energetic phase where the two black holes will coalesce. You feel the profound precision in how the universe orchestrates these events, following physical law without exception. You rest in the certainty that every calculation, observation, and simulation aligns, guiding the system toward the next extraordinary stage. And as you watch the black holes circle each other with increasing speed and intensity, you sense the approaching moment when space-time itself will ripple with maximal energy, preparing for the sudden union that will mark one of the most extreme transformations in the cosmos. You focus on the instant when the black holes finally converge. You notice that as their event horizons draw together, space-time curvature reaches its maximum. The gravitational fields combine, producing a single, larger horizon almost immediately. You understand that this fusion is governed entirely by general relativity. The laws of spacetime dictate how the two masses coalesce into one. You sense the remarkable precision of this process, where extreme energies and velocities unfold without randomness, entirely within the predictable framework of Einstein's equations. You observe the gravitational waves at the moment of merger. You notice that the amplitude reaches its peak, creating the sharp, high-frequency chirp that is characteristic of black hole coalescence. You understand that this signal represents the largest rate of change in the quadrupole moment of the system, and therefore the maximum energy flux carried by spacetime itself. You see that detectors on Earth capture this peak with extraordinary clarity, allowing scientists to reconstruct the masses, spins, and orientation of the merged black hole. You rest in the knowledge that this extreme energy release is both measurable and theoretically predicted. You now examine the dynamics of the event horizons. You notice that they do not merely touch. Their shapes distort, elongate, and merge, creating a complex geometry during the transition. You understand that numerical relativity simulations capture these deformations, predicting the precise waveform of the gravitational waves emitted. You see that the horizons settle quickly into a smooth, single shape, forming a stable black hole described by the Kerr solution. You feel the calm reliability of these laws, governing even the most violent cosmic events with exactness. You focus on the energy involved. You notice that a small fraction of the total mass of the binary is converted into gravitational wave energy. You understand that for stellar mass black holes, this can be equivalent to several solar masses emitted as gravitational waves in a fraction of a second. You sense the immense scale of this energy, yet recognize that it propagates smoothly through spacetime, obeying the conservation of energy and momentum. You rest in the certainty that even extreme energy release follows strict physical law and produces observable effects consistent with theory. You now consider the timescales. You notice that while the inspiral can last billions of years, the actual merger occurs in milliseconds. You understand that this extreme brevity produces the sudden spike in gravitational wave amplitude observed in detectors. You see that the final orbits blend seamlessly into coalescence, with no discontinuities in motion, just an abrupt concentration of spacetime curvature. You feel the calm exactness of this process. The universe transitions from slow, predictable spirals to rapid coalescence without violating any known physical law. You observe the gravitational wave propagation immediately after merger. You notice that the wavefronts carry the imprint of the entire inspiral and coalescence, encoding mass, spin, and orbital alignment in their shape and amplitude. You understand that these waves travel unimpeded across the universe, offering a direct signal of the event. You see that the peak signal, though brief, allows scientists to measure the properties of the newly formed black hole with high precision. You rest with the awareness that these ripples convey accurate information about one of the most energetic processes in the cosmos. You focus on the geometry of the newly formed black hole. You notice that it quickly stabilizes into a smooth, rotating shape, consistent with the Kerr solution of general relativity. You understand that its spin is determined by the initial spins and orbital angular momentum of the original pair. You see that the mass of the remnant is slightly less than the sum of the two progenitors, with the difference radiated away in gravitational waves. You feel the certainty of this transformation. The properties of the merged black hole are entirely predictable from the known physics of the system. You now consider how simulations reproduce the merger. You notice that numerical relativity calculations model the full nonlinear dynamics of spacetime during coalescence. You understand that the predicted gravitational wave chirp matches the observations with remarkable accuracy. You see that this agreement confirms both the extreme predictions of general relativity and the reliability of computational modeling. You rest in the calm reassurance that even the most violent cosmic events are not random but obey measurable and replicable laws. You observe the waveform structure. You notice that the amplitude rises steeply to the peak, then rapidly decays as the new black hole settles. You understand that the chirp encodes the complete history of the inspiral and merger, allowing scientists to reconstruct every detail of the event. You see that the peak represents the moment of maximum acceleration and curvature, a direct consequence of the merging horizons. You feel the precise predictability of this event, knowing that every aspect, from wave frequency to peak amplitude, follows exact physical principles. You reflect on the energy flow during the merger. You notice that spacetime itself carries the energy outward in the form of gravitational waves. You understand that no matter light or information escapes from within the event horizon, but the curvature changes propagate through the surrounding universe. You see that this process preserves the conservation laws of physics, while producing one of the most detectable phenomena in astrophysics. You rest with the awareness that even extreme events operate within a consistent, comprehensible framework. You consider the scale of observation. You notice that the signals captured on Earth correspond to events billions of light-years away, yet the waves maintain their integrity over these immense distances. You understand that this allows scientists to measure fundamental properties of black holes far beyond our galaxy. You feel the profound clarity of this cosmic communication. The universe transmits precise information about its most energetic processes, entirely through measurable, predictable spacetime distortions. You now think about the immediate aftermath. You notice that the new black hole undergoes slight oscillations in spacetime as it stabilizes, producing the ring-down phase. You understand that these vibrations decay predictably, confirming the Kerr solution and allowing precise calculation of mass and spin. You see that the merger transitions smoothly into the settling phase, demonstrating the continuity and reliability of relativistic dynamics. You rest with the knowledge that even the peak of cosmic violence resolves into measurable, ordered behavior. And as the newly formed black hole settles into its stable, spinning state, you feel the last surges of gravitational waves spreading across space, carrying a record of immense energy and motion, preparing the universe to observe the subtle vibrations and calm settling that follow this extraordinary cosmic union. You observe the newly formed black hole immediately after the merger. You notice that although a single horizon now exists, it is not perfectly smooth. Small perturbations ripple across spacetime as the black hole adjusts to its final configuration. You understand that these vibrations are entirely natural and predictable, a direct result of the dynamic merging process. You feel the calm regularity in this stage. The black hole emits gravitational waves as it settles, but the motion follows exact mathematical patterns known as quasi-normal modes. You rest with the knowledge that even extreme cosmic events leave measurable, orderly traces in the fabric of spacetime. You focus on the characteristics of these vibrations. You notice that the amplitude of the waves gradually decreases over time, a sign of energy radiating away from the system. You understand that the frequency and decay rate of the waves are determined by the mass and spin of the new black hole. You see that by measuring these properties, scientists can infer the final state of the black hole with remarkable precision. You sense the subtle elegance of this process. The violent merger resolves into a calm, predictable pattern that encodes critical information about the system. You observe how the Kerr solution describes the black hole's final state. You notice that the spacetime geometry around the rotating black hole is fully defined by its mass and spin, with no additional parameters required. You understand that the quasi-normal modes confirm this solution. The frequencies of the ring-down waves match exactly what general relativity predicts for a Kerr black hole of the given properties. You feel the reassurance of this confirmation, knowing that extreme gravity behaves precisely as theory suggests. You rest in the certainty that even after tremendous energy release, the laws of physics remain reliable. You now consider the energy carried away during ring-down. You notice that it is significantly smaller than during the merger itself, yet still measurable across vast distances. You understand that these waves gradually remove the residual distortions in spacetime, allowing the black hole to reach a stable, stationary configuration. You see that the decay follows an exponential pattern, characteristic of a damped oscillator in general relativity. You feel the precision of this process, knowing that each oscillation carries information about the system and obeys strict, calculable laws. You observe the damping of different modes. You notice that higher-order modes decay faster than the fundamental mode, leaving a dominant frequency that persists slightly longer. You understand that this behavior is predicted by numerical relativity simulations and verified by gravitational wave observations. You see that by analyzing these modes, scientists can confirm the mass and spin of the final black hole with remarkable accuracy. You rest with the quiet knowledge that the universe encodes this information naturally, allowing observers to reconstruct the event from the ripples in spacetime. You focus on the predictability of the ring-down phase. You notice that the entire process can be described by a small number of parameters, despite originating from an extraordinarily complex merger. You understand that the simplicity of the final state reflects a fundamental property of black holes. Their structure is determined solely by mass and spin. You see that this no-hair characteristic means that once the black hole settles, it retains no memory of the detailed structure of the progenitor binaries. You feel the calm certainty of this order, knowing that extreme events resolve into mathematically simple outcomes. You observe how detectors capture the ring-down. You notice that the high-frequency portion of the gravitational wave signal corresponds to these quasi-normal modes. You understand that by analyzing the waveform immediately after the merger, scientists can extract the frequencies and damping times, and thus calculate the mass and spin of the new black hole. You see that this analysis requires precise filtering of noise and careful comparison with theoretical templates. You rest in the reassurance that even after violent cosmic events, the data can be interpreted with clarity and confidence. You now consider the interplay between spin and mass in shaping the ring-down. You notice that more rapidly rotating black holes produce slightly different mode frequencies than slower ones. You understand that these variations are consistent with the predictions of the Kerr metric. You see that by measuring multiple modes, scientists can test general relativity in the strong field regime. You feel the profound certainty of this result. Even under extreme gravity, Einstein's theory provides an accurate description of spacetime behavior. You focus on the fading of the waves over time. You notice that each oscillation carries less energy than the last, until the spacetime surrounding the black hole becomes essentially static. You understand that this process represents the final stage of gravitational wave emission from the merger. You see that the black hole now exists in a stable state, fully described by its mass, spin, and the surrounding spacetime geometry. You rest in the calm knowledge that what once was a violent, rapidly evolving system has transformed into a quiet, enduring object governed by predictable physical laws. You reflect on the continuity of this entire process. You notice how the inspiral, merger, and ring-down phases connect seamlessly, with energy carried outward as gravitational waves at every stage. You understand that even the most energetic events unfold according to precise rules, allowing observers to decode their history from the emitted waves. You see that the universe maintains a profound order, even in phenomena that initially seem chaotic or overwhelming. You rest in the reassurance that extreme astrophysical events can be measured, understood, and predicted with exacting science. You now consider the broader implications. You notice that each ring-down waveform provides a test of general relativity in a regime far beyond any laboratory experiment. You understand that by comparing observed waveforms with theoretical predictions, scientists confirm that Einstein's equations hold true under the most extreme conditions. You see that these measurements also provide insights into the population and characteristics of black holes across the universe. You feel the quiet satisfaction of knowing that the cosmos is both accessible and understandable, even when studying the most extreme gravitational events. You focus on the final calm. You notice that the gravitational waves gradually fade, leaving the black hole in a stationary, stable state. You understand that the energy once carried by the oscillations has radiated outward, reaching distant regions of space. You see that the merger has completed, the violent motion subsided, and the black hole now obeys the Kerr solution entirely. You rest in the serenity of this transformation, appreciating how the universe resolves extreme phenomena into measurable, predictable outcomes. And as the oscillations fade and spacetime settles around the new black hole, you sense the persistent ability of detectors on Earth to capture and decode these signals, allowing the quiet story of the merger to be understood and measured across the vast expanse of the cosmos. You begin by turning your attention to the instruments that make these observations possible. You notice the large-scale interferometers on Earth, such as LIGO in the United States, Virgo in Italy, and CAGRA in Japan. You understand that these detectors are essentially enormous, highly precise rulers, designed to measure distortions in spacetime smaller than 1,000th the diameter of a proton. You feel the calm intricacy of these instruments, with their perpendicular arms several kilometers long, suspended mirrors, and lasers that travel back and forth, forming interference patterns that reveal minute changes in distance. You rest in the awareness that this setup transforms the faint ripple of a distant black hole merger into measurable data. You focus on the principle behind the detection. You notice that as a gravitational wave passes through the detector, it stretches one arm while compressing the other, altering the interference of laser light between the mirrors. You understand that these changes are extremely small, yet detectable with careful measurement and isolation from external vibrations. You see that scientists must account for seismic activity, thermal fluctuations, and even passing trucks or waves, ensuring that only true spacetime distortions produce a signal. You feel the patience and precision required for this work, the careful isolation and calibration that allow the universe's quiet vibrations to be captured accurately. You consider how noise is filtered out. You notice that raw data contains far more background fluctuations than actual gravitational wave signals. You understand that advanced algorithms distinguish between environmental or instrumental noise and real astrophysical events. You see that repeated detection at multiple sites is critical. When LIGO, Virgo, and CAGRA record consistent signals at the expected time delay based on their separation, confidence in the detection increases. You rest in the meticulous care of these techniques, appreciating how collaborative networks confirm the authenticity of the measurements. You now focus on matched filtering techniques. You notice that scientists create extensive libraries of predicted gravitational wave signals, derived from numerical relativity simulations of black hole mergers. You understand that by comparing incoming data to these templates, the detectors can identify events even when the signal is buried in noise. You see that the waveform's amplitude, frequency, and phase are carefully matched, allowing extraction of physical parameters such as the masses and spins of the black holes. You feel the elegance of this approach. Theoretical predictions and observational data converge to reveal hidden cosmic events. You observe the timing and triangulation involved. You notice that a signal from a distant merger arrives slightly earlier at one detector than another, depending on its position in the sky. You understand that these small time differences, measured in milliseconds, allow scientists to estimate the source's location in space. You see that combining data from multiple detectors improves both accuracy and confidence, providing a global perspective on an event millions or billions of light-years away. You rest in the calm precision of this network detection, where the timing of tiny signals yields profound astrophysical insight. You focus on how gravitational wave events are confirmed. You notice that a candidate signal must be evaluated for statistical significance, comparing its properties to the expected background noise. You understand that scientists use rigorous statistical thresholds to distinguish real events from spurious signals. You see that multiple teams cross-check each detection independently, further ensuring reliability. You feel the thoroughness and care embedded in the process, and the reassurance that every confirmed signal has been scrutinized extensively before being accepted as evidence of a cosmic collision. You now consider the role of calibration. You notice that interferometers are continuously monitored and adjusted to ensure accurate measurements. You understand that laser power, mirror alignment, and environmental factors must be maintained with extreme precision. You see that even tiny deviations could distort the signal, so automated and manual calibration processes work together to maintain sensitivity. You rest in the reliability of this approach, knowing that careful engineering allows the faint ripples from distant black holes to be captured with confidence. You observe how data is transformed into physical parameters. You notice that once a gravitational wave signal is identified, scientists extract information about the black hole's masses, spins, and orbital characteristics. You understand that this process uses the amplitude and frequency evolution of the waveform, combined with theoretical templates, to solve for these properties. You see that the results allow direct comparison with predictions from general relativity, confirming its accuracy under extreme conditions. You rest in the knowledge that observations and theory align, even in the most energetic and distant events. You focus on real-time detection and alerts. You notice that when detectors identify a likely gravitational wave event, alerts can be sent to observatories around the world. You understand that electromagnetic telescopes, neutrino detectors, and other instruments can then search for complementary signals. You see that while black hole mergers often produce little light, these coordinated observations expand the understanding of cosmic events. You feel the calm efficiency of this system, where global networks work together seamlessly to observe the universe. You now consider the importance of repeated detections. You notice that each new gravitational wave observation improves our knowledge of black hole populations, event rates, and astrophysical processes. You understand that cumulative data allows scientists to refine models, test general relativity more rigorously, and predict the likelihood of future events. You see that even rare events contribute to a growing, coherent picture of the cosmos. You rest in the reassurance that the universe communicates consistently, and our instruments, analysis, and collaboration allow us to listen with increasing clarity. You observe the challenges of extremely weak signals. You notice that even strong black hole mergers produce waves that distort spacetime only by tiny fractions. You understand that isolating these signals requires extraordinary precision in instrumentation, calibration, and statistical analysis. You see that sophisticated algorithms and global collaboration are necessary to separate meaningful patterns from noise. You feel the quiet confidence that, despite these challenges, Each confirmed detection is an accurate measurement of distant, extreme events. You focus on the transformation of raw measurements into scientific insight. You notice that detectors record minute variations in laser interference patterns, which are then processed and analyzed to produce waveforms. You understand that these waveforms encode the complete story of the merger, in spiral, coalescence, and ring-down. You see that from these data, the history and properties of the black hole system are reconstructed, allowing scientists to listen to events that occurred millions or billions of years ago. You rest in the calm knowledge that information encoded in spacetime reaches us intact across unimaginable distances. You now reflect on the combination of instruments, algorithms, and global collaboration. You notice how each element, interferometers, noise filtering, matched filtering, triangulation, and alert systems, works together to detect gravitational waves. You understand that this integrated approach allows confident identification of black hole mergers despite their extreme distance and subtle effects. You see that the precision and reliability of this process rely on both human ingenuity and rigorous adherence to physical principles. You rest in the reassurance that the universe communicates its most extreme events in a measurable, predictable, and verifiable manner. And as the waves from distant black hole mergers pass through the Earth, stretching and compressing spacetime ever so slightly, you sense the delicate and precise instruments that capture these signals, translating faint cosmic whispers into knowledge that connects you directly with the energetic motion of the universe. You begin by considering the black holes themselves. Each collision provides a window into the population of these objects across the universe. You notice that measuring the masses and spins of the merging black holes allows scientists to estimate how common different types of black holes are, and how they form. You understand that some black holes originate from massive stars collapsing directly into singularities, while others may grow through accretion or previous mergers. You feel the steady reliability of these classifications, grounded in observation and theory, revealing a population that spans many billions of years of cosmic history. You focus on the information contained in the gravitational waves. You notice that the waveform encodes both mass and spin, as well as the orientation of the binary system. You understand that by carefully analyzing these signals, scientists can reconstruct the properties of the black holes and their orbit before merger. You see that some black holes spin rapidly, while others are nearly non-rotating, indicating a variety of formation histories. You rest in the clarity of this method, knowing that even unseen, distant objects can be studied through the distortions they produce in spacetime. You observe how these measurements test general relativity. You notice that the inspiral, merger, and ring-down waveforms match extremely well with predictions from Einstein's equations. You understand that each collision probes gravity under conditions far more extreme than anything achievable in a laboratory. You see that the agreement between observation and theory provides confirmation that general relativity continues to hold true even at the most intense curvatures of spacetime. You feel the calm confidence that the universe operates consistently, even in regimes that would appear chaotic without the framework of relativity. You consider the broader implications for stellar evolution. You notice that the distribution of black hole masses and spins gives insight into the life cycles of massive stars. You understand that variations in metallicity, mass loss, and binary interactions affect the final mass of black holes. You see that by studying multiple events, scientists can trace patterns in star formation across time and space, revealing the environmental factors that influence stellar deaths. You rest in the knowledge that each gravitational wave detection contributes to a larger, coherent picture of cosmic history. You now reflect on the cosmological context. You notice that many observed mergers occur billions of light-years away, meaning the waves reaching Earth were produced when the universe was much younger. You understand that detecting these distant events allows scientists to study the evolution of black holes across cosmic time. You see that this information helps map the frequency of massive star formation, binary interactions, and galaxy evolution over billions of years. You feel the steady accumulation of knowledge, where each event builds a timeline of the universe's dynamic history. You observe the complementary role of electromagnetic observations. You notice that while black hole mergers often produce little or no light, some events involving neutron stars produce both gravitational waves and electromagnetic signals. You understand that combining these observations allows scientists to verify distances, refine models, and cross-check the physics of extreme matter. You see that this multi-messenger approach strengthens our understanding of compact objects and helps connect gravitational wave astronomy with traditional astronomical methods. You rest in the reassurance that different types of signals together provide a more complete picture of the universe. You focus on the constraints these events place on black hole formation channels. You notice that some mergers involve black holes heavier than expected from standard stellar evolution. You understand that these outliers challenge current models, suggesting alternate pathways such as hierarchical mergers, where black holes merge multiple times to grow larger. You see that by cataloging multiple events, patterns emerge, allowing scientists to refine theories of black hole growth and stellar evolution. You feel the calm reliability of this cumulative process, where repeated observation informs ever more accurate models. You consider the insights into binary evolution. You notice that the orbital parameters of merging black holes reveal information about their prior interactions. You understand that binaries can form in isolation, evolving together from massive stellar pairs, or dynamically in dense stellar environments like globular clusters. You see that the distribution of orbital eccentricities and spin alignments in detected events provides evidence for these different formation channels. You rest in the clarity that gravitational wave observations offer a direct probe of these otherwise invisible processes. You observe the ability to test fundamental physics. You notice that high-precision measurements of merger waveforms allow constraints on alternative theories of gravity. You understand that deviations from expected waveforms would indicate new physics, yet all observed events to date are consistent with general relativity. You see that these observations test gravity in the strong field, highly dynamic regime, a domain impossible to recreate in laboratories. You feel the reassurance that the universe continues to operate according to predictable, quantifiable laws, even in extreme conditions. You now consider the population-level insights. You notice that catalogs of detected mergers reveal trends in mass, spin, and frequency, illuminating how black hole binaries evolve across cosmic time. You understand that these trends inform models of galaxy evolution, star formation, and the chemical composition of stellar environments. You see that each new detection refines these statistical models, building a clearer understanding of the cosmic population of compact objects. You rest in the quiet accumulation of knowledge, appreciating how each event contributes to a larger understanding of universal processes. You reflect on the combination of local and distant insights. You notice that nearby events allow precise measurement of waveforms, while distant events sample black holes formed in earlier epochs. You understand that together, these observations reveal the evolution of black hole properties and their environments across billions of years. You see that the universe records this history in the gravitational wave signals that reach Earth, allowing reconstruction of processes that unfolded long before our planet existed. You rest in the calm continuity of these observations, connecting past and present through physics. You consider the synergy with other astronomical data. You notice that gravitational wave events complement observations of stellar populations, supernova rates, and galactic dynamics. You understand that integrating these datasets creates a coherent picture of cosmic evolution, revealing how massive stars live, die, and influence their surroundings. You see that gravitational waves provide a direct measurement of the invisible black hole population, which is otherwise inaccessible to electromagnetic observation. You rest in the reassurance that different lines of evidence converge to form a unified understanding of the universe. You focus on the educational and scientific impact. You notice that each merger is not only an event to detect, but also a source of insight into astrophysics, cosmology, and fundamental physics. You understand that by analyzing these signals, scientists can test theories, refine models, and expand knowledge in multiple fields simultaneously. You see that the merging of black holes is both a local event in spacetime and a window into universal processes. You rest in the awareness that careful observation transforms extreme cosmic events into precise scientific understanding. And as you consider the cumulative insights from countless black hole collisions across the cosmos, you sense how each ripple in spacetime carries information about formation, evolution, and dynamics, quietly connecting distant stars and galaxies to the laws of physics that govern your own part of the universe. You begin by considering the next generation of gravitational wave observatories. You notice that space-based instruments, like the Laser Interferometer Space Antenna (LISA), are designed to detect waves at much lower frequencies than ground-based detectors. You understand that these low frequencies correspond to more massive systems, including mergers of supermassive black holes found at the centers of galaxies. You see that placing interferometers in space allows them to avoid terrestrial noise, such as seismic vibrations and atmospheric disturbances, providing an unprecedented clarity in observing the slow, long-period oscillations of spacetime. You focus on the design of LISA. You notice 3 spacecraft forming an equilateral triangle with sides millions of kilometers long, using laser beams to measure minute variations in distance between free-floating test masses. You understand that gravitational waves passing through this formation alter the separations by tiny amounts, revealing the presence of distant massive mergers. You see that the technology requires extreme stability, thermal control, and precise measurement to detect signals smaller than a fraction of a picometer. You rest in the sophistication of this engineering, appreciating the delicate interplay of lasers, mirrors, and spacecraft motion that allows us to measure the universe's largest gravitational phenomena. You consider the new frequency ranges that these instruments will open. You notice that LISA and similar detectors will be sensitive to signals for months or years before supermassive black holes merge, capturing the slow and spiral phase that ground-based instruments cannot detect. You understand that this long-term observation will allow detailed tracking of binary evolution, providing insight into the environments and histories of these massive systems. You see that frequency coverage is critical. Different classes of gravitational waves correspond to different masses and separations, meaning multiple detectors operating in complementary ranges will provide a more complete picture of black hole populations across the universe. You feel the expanding reach of our observations, extending both in mass and in time. You observe the design of next-generation ground-based observatories. You notice instruments like the Einstein Telescope in Europe and the Cosmic Explorer in the United States, which are planned to have much longer arms and improved sensitivity compared to current detectors. You understand that these upgrades will allow detection of smaller amplitude waves from more distant events, increasing the number of observable mergers and extending the observable volume of the universe. You see that these facilities will also be equipped to measure subtle waveform features, improving precision in mass, spin, and orbital parameter estimation. You rest in the knowledge that both space-based and terrestrial advancements are expanding the horizon of gravitational wave astronomy. You now consider the technological innovations that make these detectors possible. You notice improvements in mirror coatings, vibration isolation, and laser stability that reduce noise and increase sensitivity. You understand that these refinements allow detection of increasingly weaker signals, including those from lower mass mergers or more distant events. You see that cryogenic cooling and underground construction, planned for instruments like the Einstein Telescope, reduce thermal and environmental disturbances. You feel the meticulous care in engineering that transforms tiny spacetime distortions into measurable data, enabling unprecedented insight into the universe. You focus on the synergy between current and future detectors. You notice that having a network of observatories, both on the ground and in space, will allow precise localization of sources and better determination of physical parameters. You understand that overlapping frequency coverage will enable continuous observation from early in spiral through merger and ringdown, capturing a complete record of the binary's evolution. You see that these observations will provide not only more events but also richer information about each one, including mass transfer history, eccentricity, and spin alignment. You rest in the anticipation of this expanded observational power, knowing that future instruments will deepen our understanding of black holes. You observe the implications for cosmology. You notice that detecting mergers across a range of distances and redshifts allows measurement of the expansion rate of the universe and testing of dark energy models. You understand that gravitational waves act as standard sirens, giving direct distance measurements without relying on traditional cosmic distance ladders. You see that combining these measurements with electromagnetic observations provides independent verification of cosmological parameters, enhancing confidence in our understanding of the universe's large-scale structure and evolution. You feel the subtle power of gravitational wave astronomy to connect local observations with universal history. You consider the study of intermediate and supermassive black holes. You notice that current ground-based detectors are limited to stellar mass systems, leaving a gap in the observable mass spectrum. You understand that space-based detectors will fill this gap, revealing mergers of black holes with millions of solar masses. You see that this will provide insight into the growth of galactic nuclei, the formation of galaxies, and the hierarchical assembly of massive black holes over cosmic time. You rest in the awareness that extending observational capability across mass ranges will illuminate structures and processes previously hidden from view. You now reflect on the role of numerical simulations. You notice that accurately predicting waveforms for the new classes of mergers requires advanced computational models of general relativity. You understand that these simulations provide the templates necessary for matched filtering and parameter extraction in future detectors. You see that improved waveform modeling will increase the precision of mass, spin, and orbital estimates, and may even allow testing of subtle relativistic effects such as precession, higher-order modes, and tidal interactions in neutron star binaries. You feel the calm confidence that theory and observation will continue to advance hand in hand. You observe the opportunities for discovery. You notice that future detectors will likely observe entirely new classes of events, such as highly eccentric binaries or exotic mergers that are currently undetectable. You understand that these observations may reveal unexpected astrophysical processes, including interactions in dense stellar clusters, early universe black hole formation, or even mergers of primordial black holes. You see that every detection provides both confirmation of existing theory and the potential for new knowledge. You rest in the reassurance that the universe has more to reveal, and that our expanding instruments will be ready to capture its messages. You focus on international collaboration. You notice that the development of LISA, Einstein Telescope, and Cosmic Explorer involves scientists and engineers from multiple countries, working together to design, construct, and operate these observatories. You understand that this global effort enhances redundancy, data sharing, and scientific productivity. You see that by combining expertise and resources, the community can maintain continuous observation and rapidly respond to new discoveries. You rest in the calm certainty that cooperative planning strengthens both the reliability and reach of gravitational wave astronomy. You consider the long-term impact on astrophysics. You notice that the combination of current and future detectors will produce an unprecedented catalog of black hole mergers and other compact object events. You understand that this will allow precise statistical studies of population properties, formation channels, and cosmic evolution. You see that the resulting datasets will also support tests of fundamental physics, including alternative gravity theories and the behavior of matter under extreme densities. You rest in the quiet knowledge that the scientific horizon is expanding steadily, with each technological advance allowing deeper insight into the universe. And as the next generation of observatories begins to take shape, both on Earth and in space, you sense the anticipation of countless gravitational waves yet to arrive, carrying precise information about black holes, cosmic evolution, and the underlying laws of spacetime, waiting to be measured and understood. You begin by letting your mind settle on the full scope of black hole collisions. You notice how gravity shapes the dance of massive objects across the cosmos, guiding each in spiral, merger, and eventual ring down. You understand that these events, though occurring millions or billions of light years away, produce waves that subtly ripple through spacetime, reaching Earth long after the collision itself. You feel a quiet appreciation for the constancy and predictability of these processes. The laws of physics apply equally near and far, governing everything from the smallest stellar remnants to the largest black holes. You focus on the gradual spiraling of the binaries before collision. You notice how the black holes orbit each other ever faster, radiating energy in the form of gravitational waves, carrying information about their masses, spins, and orbital parameters. You understand that this radiation extracts energy from the system, drawing the two objects closer until coalescence becomes inevitable. You see that these waves travel across vast stretches of space, expanding and compressing spacetime in a way that is measurable even at the distance of billions of light years. You rest in the calm rhythm of this cosmic process. You consider the coalescence itself. You notice the sudden convergence of two event horizons into a single, larger black hole. You understand that during this moment, an enormous amount of energy is radiated as gravitational waves, yet no matter or light escapes the horizon. You see that the resulting black hole quickly settles into a stable configuration, with mass and spin determined precisely by the initial components. You feel the quiet efficiency of these extreme events, observing how even violent processes resolve predictably, obeying the mathematics of general relativity. You observe the ring-down phase. You notice how the newly merged black hole vibrates and emits gravitational waves in quasi-normal modes, gradually damping to a stationary state. You understand that these vibrations carry detailed information about the final mass, spin, and geometry of the black hole. You see that measuring the frequencies and decay times of these modes confirms the predictions of the Kerr solution and provides direct evidence that the laws of physics are consistent under extreme gravitational conditions. You rest in the serenity of this orderly settling. You reflect on the role of detectors. You notice the precision of interferometers like LIGO, Virgo, and CAGRA, capturing tiny distortions in spacetime. You understand that the signals they measure allow scientists to reconstruct events that occurred far beyond our solar system. You see that advanced data analysis, matched filtering, and collaborative verification transform subtle vibrations into a coherent story of cosmic motion. You feel a gentle wonder at the capability of human ingenuity to connect with phenomena occurring across unimaginable distances, bringing the universe into perceptible awareness. You consider the insights gained from these observations. You notice how each detection informs the population, mass distribution, and spin characteristics of black holes. You understand that patterns emerging from multiple mergers illuminate the processes of stellar evolution, binary formation, and galactic development. You see that by studying these distant, invisible objects, scientists gain knowledge of the life cycles of stars and the dynamics of dense environments. You rest in the knowledge that every wave carries a fragment of cosmic history, patiently recorded and analyzed over time. You observe the broader implications for cosmology. You notice that gravitational waves act as messengers, carrying information about distances, expansion, and structure formation. You understand that repeated detections across billions of light-years allow scientists to map the universe's evolution and test the predictions of general relativity on a grand scale. You see that the combination of local events and distant mergers constructs a coherent, consistent picture of spacetime's behavior across epochs. You rest in the awareness of these subtle yet profound connections. You reflect on the integration of gravitational wave astronomy with traditional observations. You notice how electromagnetic signals, when available, complement wave-based measurements, providing additional constraints on location, environment, and energy output. You understand that multi-messenger astronomy allows cross-validation of cosmic events, confirming theories while also uncovering new insights. You see that these combined observations reveal both the violent and silent aspects of the universe, from bright supernovae to dark black hole collisions. You rest in the calm satisfaction of this comprehensive approach. You consider the future trajectory of discovery. You notice the upcoming instruments, both terrestrial and space-based, that will expand the detectable range of masses, frequencies, and distances. You understand that these developments promise to uncover events currently beyond reach, extending knowledge of black holes, neutron stars, and other compact objects. You see that as sensitivity improves, the catalog of observed events will grow, refining statistical models, population estimates, and tests of general relativity. You rest in the gentle anticipation of continued discovery, knowing the universe will steadily reveal more of its structure. You reflect on the interconnectedness of cosmic motion. You notice how even the most distant collisions subtly influence spacetime, propagating through the fabric of the universe. You understand that each event, measured and interpreted on Earth, provides a direct link to objects that existed billions of years ago. You see that the precision and predictability of these processes allow science to bridge both time and distance, translating ripples in spacetime into knowledge. You rest in the quiet assurance that the universe operates with consistent rules, offering continuous opportunity for learning. You focus on the elegance of physical law. You notice that gravity, as described by general relativity, governs motion on all scales, from planetary orbits to binary black hole mergers. You understand that the same principles dictate the behavior of spacetime near each massive object, whether isolated or interacting with others. You see that the harmony of these laws allows prediction, observation, and confirmation of phenomena that are otherwise invisible. You rest in the serenity of this order, appreciating the stability and coherence underlying the cosmos. You observe the cumulative wisdom of observations. You notice that each black hole merger, once decoded, contributes to a growing map of the universe's history. You understand that these events collectively inform models of stellar evolution, binary dynamics, and galactic development. You see that gravitational wave astronomy provides a continuous thread connecting individual events to the broader structure and evolution of the cosmos. You rest in the calm understanding that the universe communicates its processes through precise, measurable, and predictable signals. You reflect on your own connection to these phenomena. You notice that while these events occur far away in space and time, their effects propagate across the universe, subtly altering the fabric of spacetime that surrounds you. You understand that the detection of gravitational waves links you to distant, massive objects, allowing observation and measurement of events that predate human existence. You see that the universe is accessible through careful measurement, computation, and interpretation. You rest in the gentle awareness that you are part of a cosmos that is coherent, measurable, and interconnected. You consider the ongoing story of discovery. You notice that each detection of gravitational waves adds a chapter to humanity's understanding of the universe, revealing both predictable and surprising details about black holes, spacetime, and cosmic evolution. You understand that continued observations will refine knowledge of masses, spins, distances, and merger rates, providing ever more precise tests of general relativity. You see that the universe offers a continuous stream of data, patiently awaiting interpretation. You rest in the calm assurance that the pursuit of knowledge proceeds steadily, guided by reliable physical laws. And as you settle into the quiet rhythm of these cosmic motions, you sense the enduring presence of gravity, the measured ripple of spacetime, and the persistent dialogue between distant black holes and our instruments, quietly connecting you to the vast, precise, and unfolding story of the universe.